Okay, can you see that?
Yes. So you can start.
Okay, thank you so much for the presentation and all the present here. Um, this work is titled on the importance of supports when designing support catalysts in case of titanium oxide polymorphic mixes. And we are going to talk about a little bit of the outline, is the introduction, a little bit of the materials and methods uh, carried out in the experimental section, then the results and discussion, and some conclusion of this overall work. Starting with the introduction, we all know that from a classical point of view, supported catalysts used to have to focus in the metal phase, so we need small domains highly dispersed on a support that used to be a carrier for this active phase, the metal particles. But we also question ourselves, what's the support's role? So is it limited to act as carrier for metal particles, or we can achieve other features with the support? So in the case of the classical point of view, we need a high surface area to support in a small domain with metal active phase. But in a few couple of years, we could also see that some redox capacity and oxygen mobility that could be within the support, and also the interface with the metal and the support could also be active sites for the reactants are and the products. So they are also important to be taken into account as the support itself and not only the active phase that is metal. And therefore the chemical nature and the metal support interaction influence this catalytic performance during reaction. So we have some active, so-called active supports versus some traditional supports. In the active ones, we have some reducible oxides like cerium oxide, titanium oxide, and also iron oxide. And in the case of the traditional supports, we also have the alumina, it's more an inert one, some carbons, and the well-known zeolites. So to sum up, the rational design of the catalyst should take into account the importance of the support. And then we can go further. If we take the example of the titanium oxide, we know that this metal oxide could be a promoter or a carrier, a support, or a catalyst itself, mostly in photocatalytic reactions and also in oxidation reactions. And this is really used in the literature because it has high thermal and mechanical stability. Also, the redox properties are well known, this change between the valencies of the titanium, and also the availability and the low cost of this metal oxide. And on the other hand, we have the high energy ball milling that is a more or less new method, an efficient and eco-friendly method that could lead us to the synthesis of new materials, but also to improve some physicochemical properties of the materials itself, because it may introduce both structural and surface defects that could lead to polytropic transformation, for example, and also this increase in oxygen and ion mobility that are really important during reaction when we talk about catalysts. So taking all of these into account, we uh, uh, we perform this work that taking the high energy ball milling on one hand, trying to produce some polymorphic transformation of an anatase phase through the different polymorphs. So changing some parameters of the milling, we could have on-demand mixtures with higher properties, with enhanced properties, such as the external surface area, the oxygen vacancies, and also the reducibility and the oxygen mobility of these materials. That all of these improved properties could be really used as core as catalyst support, for example, in oxidation reactions, both in gas phase or liquid phase. So we started this study with a titanium monoxide, a pure anatase phase with low surface area, and we used a planetary ball mill in the that here in the image we can see that planetary mirror, and also we changed some parameters like the rotational speed of 350 rpm and 500 rpm, and of course the milling time that could produce more energy in the system and perform the changes more faster. And we have all the materials obtained were named like TXY, where X corresponds to the rotational speed, and the Y corresponds to the milling time. So with some results we obtained, we performed some X-ray diffraction to have an insight of the crystalline structure of the materials obtained, and we started from the analysis phase, passing through the different polymers to obtain a final rutile phase that is the thermodynamically more stable form of the titanium oxide. So we obtained some unusual mixtures of these three polymers according to the milling time, which was really interesting. We could see that from the reflection lines from the XRD. This is the case of the speed of 350 rpm. In this case, we obtain the same transformation at 500 rpm, but in a faster position. The same polymer, but in a faster way. Then we went through some calculations of some rough estimation of the composition of each of these three polymers, taking the equations from the literature and the most intense reflections of each of the crystalline phases. And we also estimate the average crystalline size, and we could have some values in accordance with the milling time. And this is like that because the milling time and the structure of the made in the milling could define the particles and therefore, as consequence, increase the surface exposed. So we have some lower crystalline sizes and an increase in the surface area, as you can see here. And we could double this starting value of 8 meters per gram, square meters per gram, with the milling time, and also obtain some pore diameters that were high enough to avoid internal diffusion limitations, because if we use big molecules, it could interact with the porosity and it would be difficult to diffuse within the pores. So in this case, the pore diameters were high enough to avoid this limitation. And also, sorry, the total pore volume were lower, and this is the common thing because the titanium monoxide has a really low porosity. So, then we have some microscopy, some transmission electron microscopy, and we could see the titanium, this phase that is a metastable phase that is observed at high pressures commonly. And we could observe that in the same positions as in the anatase phase. So it was formed at the surface of the anatase grain, because it was formed at the expenses of the anatase during this polymorphic transformation. And then we could observe some more micrographs, and we could obtain these both polymorphs separated. So the rutile could be obtained in different grains and not linked to the anatase. So the polymorphic transformation should be from anatase to rutile passing through this intermediate that is the titanium oxide 2 high pressure phase. And it was really interesting because it is a and we could have some mixture of the three phases in the same material, which is uncommon in the literature because commonly they use a support the titanium oxide with a pure structure, maybe anatase or rutile in the pure phases. We also made some XPS, and we could observe some oxygen vacancies as well generated at the surface, but that could disappear during the milling time in order to promote this phase transformation in the bulk and progress in this polymorphic transformation. So we have a trend in a reduction trend in this oxygen vacancies. But also it was interesting to have an insight about these vacancies, and we performed some electron paramagnetic resonance. And in all cases, we obtain signals with the major polymorphs. We can see these two spectra are similar, and these were these samples have anatase major phase. In the case of these two, they are also both similar, and they have this high pressure polymorph in a composition of 50% average. And the last of the samples is a pure rutile, and it's really different from the others. So we obtained these signals with these values of G that were associated with the presence of titanium, reduced titanium with glass imbalance from the bulk but not the surface, which could sustain this surface oxygen concentration that I talked before from the XPS study. And then finally we performed some program analysis, and we, in the reduction, the reducibility of the materials was performed, and we obtained a higher reducibility starting from this material. We could observe the signals associated to titanium monoxide at the bulk reducing at higher temperatures with these values here. And these signals at lower temperatures could be associated to surface titanium monoxide that could be reduced. And also the uptakes of hydrogen were higher according to the living time. So these effects and microstructure that is effective with lower crystalline size could be more reducible. So the living type could perform a better properties in the physical titanium oxide. And also we obtain some values of the oxygen that could be absorbed in oxygen vacancies, some signals that also increase the milling time. And in this case, some bulk oxygen of the lattice that also we have some signals to compare to the starting material. We could observe an enhancement, an improved oxygen diffusion, and also the visibility that in our particular case could have a major role, a detrimental role in oxidation reactions, because we need this motility of the oxygen and a good reducibility to perform this cycle, this redox cycle during the catalytic reaction. So in conclusion, we could obtain titanium support with on-demand phase composition through this high energy bond milling, this mechanochemical method that is really used nowadays. The external surface area was doubled due to particle refinement. So this is an advantage because we could use these new materials as support for metals and particles. Also, the oxygen vacancies were promoted and greater reducibility and oxygen mobility and reduced CD4. And also this unusual high pressure phase and the equilibrium between these phases remain stable under harsh conditions. In fact, we perform some oxidation studies to see if this composition remains stable even under high pressures and in aqua media. So they remain stable even under high pressure of oxygen. And therefore, these solids with enhanced viscochemical properties could be successfully used as a catalyst support. And related to this, some palladium batteries were prepared with this support and are now being tested in glycerol selective oxidation in liquid phase to study these metal support interactions and of course the catalytic performance during the oxidation. So these are the acknowledgements from Argentina and Spain on the financial support. And thank you very much for all of your attention.
Thank you very much, Matias. Thank you for your presentation about Titania. It has been very interesting. If some of the participants, do they have any